If you're a CNC programmer, there's something you're doing wrong every day at your company and you don't even realize it. Now, if you already own the company and have a CNC machine, your machine is probably producing way below its potential and you're leaving money on the table. And the good news is that there's a simple way to fix this. And I'm going to show you now. When we talk about CNC machines, of course, we're talking about high productivity. And then you buy the best CNC machine you can buy. You invest in work holding, in cutting tools, a preset, a probe to reduce setup time, machine downtime. You buy CAM software to reduce machine downtime with programming right at the machine. I have all of that here. This setup has all of it, but there's one detail that most of you don't know, which can greatly reduce machining time. You can produce more and consequently earn much more. I'm going to run 2 tests here. I have a part clamped in the vise and I'm going to run the first program, the first part, using traditional machining, which is what programmers commonly do on a daily basis. But I'm going to take this same program and make some small adjustments to it. I'll use specific software for that, and then let's see what happens with the part time. And I think we'll be able to increase productivity and you'll automatically be able to earn more. Now I'm going to show you the mistake you're making every day. And this mistake is called the cutting parameter. But hold on, you might not even be calculating the cutting parameter wrong. I believe you're not. But there's a detail that if you adjust it, you'll already save a lot of time in your machining. Shall we start by understanding how the cutting parameter works? For the CNC machine, I need to provide it with 2 things. What is the spindle speed the tool will operate at? And what is the feed rate for that tool? The spindle speed refers to the tool's rotation and the feed rate is the movement of the table. So let's start by calculating the spindle speed. To calculate the spindle speed, we use this formula here. We then proceed to multiply the cutting speed by a specific constant value. We typically utilize the numerical value of 318, which is precisely derived from the mathematical operation of 1,000 divided by the constant p. Subsequently, we perform the division of this result by the precise diameter of the cutting tool being employed. Up to this point, it's straightforward. You're using this information, working the right way, and finding the correct spindle speed parameter for your tool. Now, the next parameter we need to find is the feed rate. To find the feed rate, I need to know how many inserts the tool has. So the calculation is very simple and straightforward. We are going to meticulously use the fundamental formula, feed per insert, multiplied by the total number of inserts, and then multiplied by the RPM, which I precisely found using the previously established and applied formula. That's it. This is the correct way. If you're doing this, you're already doing it the right way. And then, when it's time to do your programming, you'll enter this data and run your part. Are you going to do a facing operation? Enter this data, run it. If you're going to do a contour, run it. But there's a hidden problem that you're not seeing, and I'm going to show it to you now. I have programmed this particular part in SolidCAM. And it's important to notice that here I will have several distinct processes. I have various contours, precise drillings, and intricate keyways. So I have carefully downloaded all the necessary tools directly from the official ISCA website, and this entire setup here will be the comprehensive machining process. So I will have a primary facing process, and I will have several other important processes on this specific part here, and you will closely follow along with me. This process is the traditional machining process that we do inside companies. You set a feed rate, set a rotation speed, and the tool follows the path that needs to be done using that rotation and feed rate. Then I'm going to take this same program. I'm going to put it into Vericut's Force, and Force will optimize the same program that went to the machine. You'll follow along with me to see what will happen in this machining process. So come with me, because now we're going there. To set up the machine to make the part, this is the piece that will be machined. This is a steel block, 1045. I'm going to machine it using the traditional process. Then we're going to face and machine a bit more, okay? With the process optimized by Vericut's Force. Shall we? With the part securely clamped in place, it is now the opportune moment to precisely set the part 0 for machining operations. Since the part is already zeroed, I'm going to use 6 tools in this process. I'm going to run my program with automatic preset. And I'm going to have my usual cup of coffee. Let's go. Everything's ready. Now it's just a matter of running the program. How did I do this programming? In SolidCam, the post-processor for this machine was developed by SolidCam itself. I'm just going to close the door and run it. That's one of the advantages of using licensed software, because the post was developed by SolidCam itself. Let's run it. I'm now running a facing process, and notice with me that I'm advancing. It's consistent throughout the entire facing of the part. In this process, I'm now machining the contour of the part. This is the most time-consuming process. And follow along with me to see what's happening here on the panel. I have a constant feed rate. And this constant feed rate is the problem we're going to solve using force from Vericut, and we'll be able to optimize this machining. This one's finished, and now let's see how it turned out. The quality is excellent, but now what's more important, let's see how long it took to machine this part. It took 9 minutes and 27 seconds. Now, why did it take 9 minutes and 27 seconds? I worked with the correct cutting parameters, with good tools, and I got all the data from the tool manufacturer's website. Can I still improve it? That's exactly what we're going to do. We're going to improve this part's machining time using the same program that was run here. And I'm going to show you where the bottleneck is, where the problem is that's leaving money on the table and increasing your part time on the machine. By default, we programmers, when you're going to do a machining process, you set a feed rate for the tool. And the tool works on the entire part with that same feed rate, depending on each process. But there's something that many programmers don't see. And I'm going to show you right now in the software. I'm going to simulate a precise facing operation on a specific part, and I invite you to watch with me closely what precisely happens during this intricate facing process. In this initial crucial first pass, I am carefully removing material that is a little less than 50% of the entire tool's diameter. But in this subsequent, more aggressive second pass of the tool, I am removing a significantly greater amount of material. Here, I have an area that represents approximately 50% of the overall tool's capacity. The exact same phenomenon occurs during the third pass of the facing operation. However, in the fourth and final pass, I observe a very small facing area, indicating a precise and refined stage of the process. What happens is that when I have less area for material removal, I can keep increasing the feed rate of the tool. What's happening here? I have one area with very little material, two areas with 50% of the tool, and one area with about 40% of the tool. And all these areas, you are working with the same feed rate, with the same tool speed, whereas I could have different feed rates for different steps. Just in facing alone, that would already save me time. Now let's look at a contouring process where this problem is even more serious. Come with me. Here I have a contouring process. You can see that here this problem is even more serious for a few reasons that I'm going to show you now. Notice that in this part I have an area with very little material to be removed. I have an area with a bit more material to be removed, and I have a very large area of material to be removed here in the four corners, so that I don't have problems when I reach areas with a lot of material to be removed. It's normal for us to lower the feed rate taking these large areas into account, and that way the tool works slowly throughout the entire path of the part. Where I have areas here where I'm removing 1 millimeter from the wall, and in other areas 3 millimeters, I could have a much higher feed rate in these specific areas and a lower feed rate where the software detects that there's a lot of material to be removed, and that's exactly what Vericut's force will do. But in this same part, I have this problem happening several times. Come with me to see this in another process. After being rough machined with the first tool, the part looks like this. But when I analyze the remaining material, I can see that on this wall there's little material left to be removed. However, since there's going to be a radius reduction here, there's a lot of material to be removed. This is a problem. Now, why is this a problem? If I keep a high feed rate because the wall has little material, when I hit the area with a lot of material and a carbide end mill, I'll tend to break the end mill or even have vibration issues. All this happens because I keep the same feed rate throughout the entire path of the part. Whereas in reality, for more efficient machining, I need to use variable feed rates depending on the amount of material to be removed, as is the case here. Reduce the feed rate when reaching this area and increase the feed rate when reaching this area. Do you think that's all? It's not over yet. There's a keyway process on this part, and you'll see that you make keyways several times a month and never paid attention to this problem. Come with me. Here I have a traditional keyway machining process for cutting keyway slots. And now look at what happens in this situation. While the cutting tool passes precisely through this particular point, it effectively removes its entire full diameter of material when it is steadily moving in this specific direction. However, when it comes back to continue the cut and make the overall width of the keyway, here less than 20% of the tool is in contact with the part. In other words, at this point I could use less feed, and at this point here I could use more feed. On this part I have 6 processes where I should have variable feeds for each one of them. That is, more feed, more productivity, and the part spends less time on the machine. But the point isn't just to increase the feed. It's about how much I should increase the feed. This has to be linked to the tool, the material, and the chip removal. If I know this information, I can increase the feed at specific points, achieve greater productivity, and still increase the lifespan of my tool because it will always be working within the correct parameters with the correct average chip thickness for each removal. And that's exactly what I'm going to do now inside Vericut's force module. I'm going to take this program, the very same one that was run on the machine, just as it was executed, load it into Vericut's force, and request an optimization of this program. And there are some very important points I need to inform it here, and I'm going to show you now. Come with me. This is the Vericut software. At this particular point in time, I have the complete CNC program that was meticulously executed on the machine, already fully loaded into Vericut. I've also carefully loaded all of the essential tools that were specifically utilized in my program, every single one of them, and I have successfully loaded all of the detailed 3D models of these various tools so I can effectively work with them and manipulate them as needed. One important thing to note here is that I define the specific material of the part to be machined. Vericut has a comprehensive list with various materials from different classes where I will carefully select the precise material I'm machining. In my particular case, my material is 1045 steel. With this information, now I'm going to enter force and start optimizing, and it's very simple. Basically, I've already provided the material, the tool characteristics, what my raw material is, my CNC program. Vericut will analyze all of this and optimize my CNC programming, increasing feed rates where it's possible to go faster, and reducing the feed rate in areas where there's going to be a lot of material removal. This would be harmful to the tool. This is something I can't do manually. Sure, I can increase or decrease the feed rates in my CNC program, but it would all be guesswork. That's not the case here. It will calculate the average chip thickness, cutting force, and give me an optimized program. Come here. I'll show you how we're going to optimize this now. With all the information loaded, I'm going to enter optimization control, and I'll select that I want to learn from the NC program. What does it mean to learn from the NC program? Vericut will run the entire program, understand the toolpath, where there is more effort, where there is less effort, and it will perform this optimization by adding variable feed rates to my program, which previously only had one. Constant feed rate. And here it's very simple, just a few clicks. Come with me so you can see. I'm going to select the location where the new file will be saved. And I want it to calculate chip thickness and force, especially EA, percentage of learning. I want it to be aggressive. Just apply, click OK, and now I'm going to select the Optimize button. Notice that the simulation will start, and now Vericut is learning from the CNC program. The entire CNC program will be executed by Vericut. It will be read, all the cutting forces, chip thickness, chip average. Vericut will understand all of this to give me an optimized program. But there's something even cooler. Here, while it's still optimizing, I can show you this. Come here. I can open a graph, understand what Vericut is doing. I have two graphs here, one for chip thickness and another for force. Notice that in this graph, I have peaks, and all these peaks represent cutting forces, forces on the material. Where I have these distinct valleys here, these are specific points where Vericut can effectively work to consistently keep the machining force always constant and optimized. And to keep the force constant, since I have variation in material removal, what do I need? I need to change the feed rates. Now I just have to wait for Vericut to do its job, give me this optimized program, and I'll load it into the machine so we can run it and see what the actual time savings are. With software where I made just a few clicks, and the software's intelligence will calculate this and give me an optimized program. But I want to see what kind of improvement it will bring. The Vericut optimized program is already on the machine. I'm going to run it on the same material. However, since I've already done the first machining in the traditional way, I'll do a facing operation to remove that machining, and then I'll run the optimized Vericut program. And we'll be able to measure what the actual time savings are here. Now I'm going to do the facing. Come with me. The part is already faced, and now we're going to put this very cutting force to the test. I have to admit, I had never seen CNC program optimization of a finished G-code like this before. I don't know what the result will be. They say it's really good, but we'll see in practice. That's why I machined it the traditional way, optimized the program with Vericutting's force, and now I want to see the results. Here on the shop floor, at the machine, what will the outcome be? Let's get it running, even I'm anxious to see. I'm already noticing the first change here in the facing operation. When do I come here? In the program, several feed rate lines were added here, and the feed rates are quite varied. So I have the feed rate increasing, then decreasing. All of this is happening during the facing process. But I'm curious to see what happens during the contouring process. Because there, it's very clear that more material is removed at some points and less at others. Let's wait and see how this process turns out. Now look at this. How interesting. This was the part that I wanted to see. Where the walls are straighter, the feed rate speeds up. Where there's a curve, where there's more material, it slows down. Come here so you can see how the program turned out. Notice that there's a big variation in the feed rate. Here are the lines. You won't be able to see them because it's too fast. But take a look at the process in practice. Besides all that, there's something else here that I find even more interesting, which is this. In the traditional process, when I started going through a curve, removing more material, I would get vibration. Now I don't have that vibration anymore. The speed is so well controlled that I don't get vibration on any of the parts profiles, whether I'm removing a little material, a medium amount, or a lot of material. That really impressed me. Now the 10mm end mill is going to come in. And this is an interesting point. There's a reduction in radius there, and I want to see how the program behaves, how it's going to handle it now. Here it's worth noting the variations in feed rate along the toolpath. And this feed rate decreases when it's in the radius. Now in this process, it's machining the keyway. And here it's very clear to see that. Follow along with me on the control panel. While the keyway cutter is taking a full cut, it has one feed rate. When it's only cutting half the material, the feed rate changes. This is the completion of the force optimization. And first, I want to see how the part turned out. Come take a look with me. The quality of the part, I dare say it turned out even better than the previous one, especially in the radii, where there was a greater tendency for vibration. More material was removed. The finish inside the keyway also turned out very good, as did the contours of the chamfers. I like this solution, it was surprising, but now what I want to understand is the time. That's what's most important. Let's see how much time we saved with this optimization, if we actually saved any, right? Come check it out with me. And the total part time after optimization was 7 minutes and 17 seconds. Look, from 9 minutes and 27 seconds down to 7 minutes and 17 seconds. That was a considerable reduction. We're talking about 2 minutes and 10 seconds per part, and I didn't have to do anything. I simply took the text program, ran it through Vericut's force, it optimized it, and then I took the same program and loaded it into the machine. But when I say 2 minutes and 10 seconds, it might seem like very little per part, right? But we're talking about a 23% reduction in time here. Imagine your company producing 23% more, or your salary, if you're a CNC programmer, earning 23% more every month. Because if we increase this a bit by 2 minutes and 10 seconds over an 8-hour shift, we're talking about 16 more parts every day, and by the end of a week, we're talking about 80 extra parts. If I take this over a month, for example, then we're talking about 320 extra parts, simply by taking the LC program, running it through Vericut's force, having it optimized based on the toolpath and the material, then it gives me back the program and I run it. It's practically the same program on the machine, just with the feed rates changed. I have to admit to you all that I, Fernando, was really surprised. This is one of the coolest tools I've seen lately, especially because this program was made in CAM. But this optimization can also be done on programs that were run on the machine, that were created on the machine. And this part was still a very simple part. Processes that we do every day, contour, facing, keyway slotting, chamfering, this is a basic process. Now just imagine that. Applied to a mold, for example, where you have hours and hours of machining, 23%. That could be the pickup truck you wanted to trade in at the end of the year, or the vacation you wanted to take with your family. But Fernando, my company doesn't have that much work to reduce in this way. Here's what you do. Leave work an hour earlier, since your production will be faster. Spend just 1 more hour with your family, pick up your child from school. 23%, my friend. That's a lot. I recommend you get to know Vericut Force and learn more about it. I think every company and every programmer should know about a solution like this. If you enjoyed this content, subscribe to our YouTube channel and turn on the notification bell down below. That way you'll be notified of all our new content. Join us, send in your suggestions. I'm here, bringing you top quality content, whether you're a machine programmer, CNC operator, or even a business owner. We're in this together.